The law of Biot Savart states that at any point P, the magnitude of the magnetic field intensity produced by the differential element is proportional to the product of the current, the magnitude of the differential length, and the sign of the angle lying between the filament and the line connecting the filament to the point P, at which the field is desired. Also, the magnitude of the magnetic field intensity is inversely proportional to the square of the distance from the differential element to the point P. It can also be said using vector notation as dH equals to the cross product of IDL and AR all over 4 pi r squared equals to IDL cross product of R 4 pi r cubed. And it can be also said as dH equals to IDL cross product of AR all over 4 pi r squared. The law of Biot Savart is sometimes called Ampere's law of the current element, but we shall retain the former name because of the possible confusion with Ampere's circuital law. In some aspects, the Biot Savart law is reminiscent of Coulomb's law when the law is written for a differential element of charge, dE equals to dQ AR all over 4 pi permittivity R squared. It is impossible to check experimentally the law of Biot Savart as expressed from the first two equations, because the differential current element cannot be isolated. We have restricted our attention to direct currents only, so the charge density is not a function of time. You can see as in equation B times J equals to negative dP over dt. Therefore, shows that B times J, that product of J equals to 0. Upon applying the divergence theorem, the integral of J ds equals to 0. The total current crossing any closed surface is 0, and this condition may be satisfied only by assuming a current flow around a closed path. In this, it is current flowing in a closed circuit which must be our experimental source, the differential element. The Biot Savart law may also be expressed in terms of distributed sources such as current density and surface current density. Surface current flows in a sheet of vanishing small thickness, and the current density measured in amperes per square meter is therefore infinite. Surface current density, however, is measured in amperes per meter and designated by K. If the surface current density is uniform to the total current I, in which width B is I equals to KB, where we have assumed that the width B is measured perpendicularly to the direction in which the current is flowing. For a non-uniform surface, current density integration is necessary. I equals to integration of K dN, where dN is the differential element of the path across which current is flowing.